Hi everybody, this is Mrs. Ewald signing in, and today we're going to talk about colligative properties and Raoult's law, which is just super fun to say. So just to recap where we've been talking about solutions, we've talked about concentration, molarity, how you could have different amount of moles per liter, and how solute affects things. So what we're going to do is continue on with solutes, and specifically with colligative properties. We're going to be talking about properties that depend on the number of particles dissolved in a given mass of a solvent. And here we're talking about the number of particles. Not necessarily the type, but just the amount that you have in a solvent. So some examples of colligative properties then. What I'm going to be talking about today is with vapor pressure lowering, and that is Raoult's law. And so the idea that by adding a solute, you're able to lower the vapor pressure, and I'll explain that in a minute. So this is what we will cover today. Then there's also boiling point elevation, which makes more sense after you understand what a colligative property is, and also freezing point depression. So Miss Heaton will take you through boiling point elevation and freezing point depression in the next podcast. What's great about learning colligative properties after you learn solutions is that this is all now an application to what you've learned, because it deals with real life scenarios like, why do we put salt on the street when there's ice? Or why at higher elevations do you need to have a different boiling point to boil water? So these are all realistic things, so hopefully this will give you a good application to it. So let's start off just by talking about vapor pressure and what that is. Okay, and I have some visuals to go along with it. So vapor pressure, that is the pressure exerted by a vapor that is in equilibrium with its liquid in a closed system. So, and what I mean by a closed system, I know this is not going to be the best drawing, so bear with me. Let's say that we have a bottle and we put a cork in so it's nicely tight, and you have, water in there or solution of something. So you're going to have these molecules in there, say water molecules. You're also going to have those water molecules also vaporizing. So you're going to have water as both a gas then and as a liquid, and it's also going to go back and forth into the solution. So that's going to form a gas, and then it's going to go form the liquid again. So it goes back and forth. So if it's at equilibrium, the pressure is going to be the same, both up and down. So what happens then if you add a solute? So vapor pressure, so the pressure here in a closed system can be lowered when you add an ionic solvent. Ionic meaning it's ions, and ions, for example, sodium chloride, remember those are going to break apart into sodium ion and chlorine ion. And so really it's based off of how many ions you're adding, and so that is why we say the number. So the more ions you have in your solvent, it's going to affect the vapor pressure even more. So let me visually show you over here what I mean by that. So here we have pure water, as I was kind of showing you over here, but this was in a closed system. So you have the vapor pressure, and so you have water molecules that are forming gas, and then gas molecules that are forming water liquid. So what happens then when I add a solute? So let's say this here is going to represent my sugar. So in this case I don't have ions, but I have a solvent. This would be what you call a non-electrolyte, meaning that it doesn't have ions. It's going to stay together. So this is covalent. It's going to stay together as one piece, and we represent that here. So when you add this solute into the solvent, you're going to have greater attraction now between that solute and the water. So the water is going to want to try to surround that solute. What does that do? Well, now because that water is more attracted to that solute and kind of form around it, that means you're going to have less water vaporizing. So it kind of traps it all in. This then is going to lower the vapor pressure. VP, we'll say. So by lowering that vapor pressure, what does that mean? Well, it's because this solution now has become more stable. And so the water is going to remain more in the solution than it will form into a gas. So it makes the solution stable. What does this mean? It's going to require more kinetic energy. We measure that energy with temperature to evaporate the solvent. So for you to get rid of that water and have it evaporate. So that means it's going to need a higher boiling point in order for it to get it to boil. And also you're going to need to remove more kinetic energy in order for it to freeze. So it will decrease the freezing point. Again, this is something Ms. Heaton will go in greater detail about. So over here you're able to see just another visual of that. In an ideal solution, the forces between the solvent molecules are exactly the same as the forces between the solvent and solute. So that means that it takes the same amount of energy for the solvent molecules to break away from the surface in either case. Okay? So when we look at by adding ions, so here we're looking at adding the salt. This salt now is going to break up, and you're going to have more ions because you have the sodium ion and the chlorine ion. The water is going to surround it, again trapping the water in, so you're going to have less evaporation, again increasing your boiling point. So water molecules are going to form shells around the ions, and then these shells are going to block the molecules from escaping to a vapor state. So this here is your salt, and the water is going to trap in those ions, preventing it from evaporating. Again, lowering your vapor pressure. And that's what it's going to cause the other colligative properties. So in summary of this effect is proportional to the number of particles in a solution. So the more ions you have, that means then the more solvent is going to be trapped, and so you're going to lower your vapor pressure even more. A molecule that dissociates into ions has more particles than a molecule that doesn't. So like we saw, if you have something that is covalent, it's going to remain, if I could spell it correctly, covalent, it's going to stick together like C6H12O6. It's going to remain as one piece. Versus something that's ionic, it could break up into multiple pieces. Depending on how many ions are present, that's going to affect the vapor pressure even more.